Hey everyone, welcome to week 7 of CS 109 discussion section. This is our 6th time together. Today we are talking about summing random variables and a little bit about Bayesian networks. Can everyone see my screen? My whiteboard? Great. Okay, thank you. Okay, so for this first question, we have the sum of two random variables, and this question was a little bit difficult, actually. The full question. The first part was easy, and the first part was sort of demonstrative of why we like having certain kinds of standard distributions, because the next questions are more difficult. So for this first one, we've got x distributed as a normal. Let me make my own whiteboard a bit bigger. Okay, we've got x is distributed as a normal mean 1. Yes. Move my tab thing. There we go. So mu1 sigma squared 1, y is distributed as normal mu2
Hey, Tim,
sigma squared 2. Yep,
are you drawing on the whiteboard?
I am.
I don't know if I'm the only one, but I'm not seeing anything.
Bummer. But you saw it before. Let me try this again.
It's just an empty whiteboard.
Can you see it now?
Yes.
And can you see me drawing?
Yeah.
Great. Okay, sorry about that. So we got two random variables. They're both normal. What happens when we take this new random variable and ask about its distribution? So the sum of two random variables, is itself a random variable, and it has some distribution. Does anyone know what its distribution will be?
Normal.
Still a normal, yep. And what happens to parameters?
Add the means together.
Yeah, it's really easy in this case. mu1, mu2, sigma squared 1 plus sigma squared 2. Okay. Worth noting that whenever you have, oh, by the way, these are independent, right? Independent. That's important. Independent. If you have any random variables that are independent, and then you add them, the new mean of that new random variable will just be the sum of the two, right? And we remember this because expected value of x plus y, right? We can apply linearity of expectation. In fact, linearity of expectation applies even if they weren't independent. So this is like just a truism, right? And then we have this variance of x plus y, right? And if they're independent, so this case only happens when they're independent, well, then that can be split up into variance of x plus variance of y, right? So at first, this might seem like a not very remarkable thing, but remember that the remarkable thing about this is that the new distribution is still normal. That's the key here, okay? That's a really handy thing about normals. When you add them together, it's not just that the means and the variances add, but it's that the new distribution is normal, okay? So in this other situation where we have a pair of uniform distributions, let's say x is distributed as uniform 0 1, likewise for y. Oops. Likewise for y, uniform 0 1. Well, we know that, like I just said, since they're independent, the means add and the variances add, but do I know what the distribution looks like, right? Like, what is this? It's distributed as mystery, right? Mystery with some parameters, right? And distributions are parameterized in different ways. So if it's not parameterized by its mean and variance, then we don't even know what to put, right? It turns out that this distribution is going to look something like, let me separate this out. This distribution is going to look something like this. Well, let me start off with the regular. We got the regular normal, right? And we got the other normal, right? The sum is going to look like this. It's going to be like a triangle. And this sort of equation is going to look like this. It's going to say f of x plus y of like some value a is going to equal a 2 minus a and 0 for a. Let me move my whiteboard a little bit so I can draw. A for 0 less than a 1 for a 1 2 and then for a greater than 2, or I'll just say else. Okay, so it's going to be this piecewise function. How is this sort of thing derived in general? Well, for that last part, we have, let me make this smaller again. We have the general form is something like this. F plus y a equals negative infinity to infinity f of x a minus y f of y dy. So this is actually the general, this is actually the general form, right? And this is called a convolution. The convolution is a way of summing random variables when you know that they're independent. But when you actually evaluate this for particular distributions, and in this case uniform, right, you'll get something that looked like this. You'll get something that looked piecewise like that when you work it all out, when you work out all the math. But that's super difficult, right? It's like super annoying to have to deal with calculus, especially now that we're in probability. We're past it, right? So the nice thing is that, you know, people ask often, why are we covering all these distributions, right? The binomial and the geometric and the Bernoulli and all these other ones. And the reason is because they have standard distributions that are parameterized, right? And they also combine in standard ways that make our lives a lot easier when we're trying to assess multiple random variables of the same kind, right? Whereas this uniform distribution is a lot more difficult, and it's this piecewise thing, all right? So just keep that in mind. This is sort of a lesson in the fact that you need to appreciate why we've covered the certain distributions we have, and that in the case of normals, it's super easy. In the case of many others, it's also very easy. Okay, let's jump to general inference. So if there, we sort of, it says we abuse notation, and we say, let's say we had, you know, we're asking the following question, right? x1, comma, x2 equals little x2 through x4, right? Through x4. And we're going to say that this, we're going to abuse notation and just say, well, I'm going to call this 1, 2, 3, 4. Okay, I'm just going to say that for simplicity because I don't have much time left. Okay, so if I ask you the question like, how would you split this up into more manageable chunks, right? One of the ways you could break this up is by using the chain rule. So you could say P of 1 given 2, 3, 4 times the probability of 2, 3, 4, right? Then you could notice that this 2, 3, 4 can be split up again. So that will go 2 given 3, 4 times 3, 4, right? And then you could split up that again. And then you could get 3 given 4 times 4, okay? But notice that I could have split it up a different way. So the nice thing about the chain rule is that you can think about it, since this is asking about the intersection of all these different events, right? Was the probability of x1 and x2 and x3 and x4. You can move the operators around, right? And this is really just the same thing as, you know, 3, 2, 4, 1, right? You could do it that way. And then, you know, you could split it up this way if you wanted. You could say 3 given 2, 4, 1 times probability of 2, 4, 1. And you could continue like this, right? That would split, right? That would split, and then that would split, and then it would like split again. So you could also do something like that. And that's equally valid. Both of these are valid applications of the chain rule. But for the second question says, well, what if they're all independent? What is it going to look like? And what you'll notice is, since they are all independent, and we weren't very explicit here, but when we say they're all independent, we mean mutually independent. So any subset of x1, x2, x3, x4 are independent of each other. Okay, that's what we meant to imply here. So if that is the case, then 3 given all these things that it is independent of, well, that'll just disappear, right? And then when you break that up, you'll have 2 given 4 and 1. Well, the 4 and 1 will drop off, right? Etc. Probably easier here. So like that will disappear, that will disappear, that will disappear, right? And then you'll just be ending up with probably a 4 times probably a 3, 2 times 1, right? And that's a familiar rule we are accustomed to, where 1, probably a 2, probably 3, probably 4. It didn't matter how you broke it up with the chain rule, you would observe this pattern, right? Okay, now this last one, and I don't want to take too much more of your time, but this last one is with a Bayesian network. And it said, let's say that network looked something like this. If the network looks something like this, then remember that this indicates not just the dependency relationships between variables, right? So in other words, like, 3 is, it depends on 1, right? But whenever you see a Bayesian network, it's almost always going to be accompanied by a table or a series of tables for each node, actually. So we'll say, like, this has some distribution, right? Let's say it could either be a 0 or a 1, and it could be like 0.3 and 0.8, right? It didn't have to be this Bernoulli here, but I just did it for convenience. Likewise, this could be like a 0 and a 1, and this could be 0.1 and 0.9. And sorry, these should add up to 1. My apologies. So it should be 0.7. This table, right? This will be, the way you can draw this is you put both the parents on the other side. So like parent 1, parent 2, and this could be 0, 0, 0, 1, 1, 0, 1, 1. And since it has 2 parents, like this 3 can be one of these 2 values, right? And so 0.3, 0.7, 0.5, 0.5, etc. Like some table, right? Fill in the rest. So this table, like for 4, for example, is always going to be 4, like x4 given x3, right? This table is going to be x3 given x1, x2. And then this is going to be just x1. That's just going to be just x2. And when you expand out the chain rule, as we did like on the previous slide, right? Because of the dependency relationships that we'll encounter in this Bayesian network, we're going to have p x1, p x2, p x3 given x1, x2, and then p of x4 given x3, which matches these tables, right? That should be 2. Sorry about that. Okay. And this just has to do with the dependency relationships that this Bayesian network encodes. So remember, at Bayesian network, you'll have tables that represent conditional distributions, and this will help us. So if you if you derive this from the chain rule completely, right, you might have other stuff here, like you might have an x4 here, right? But the x4 would drop out. You would notice that it would drop out because of the way that these dependencies work. X3 will be conditionally independent, right? Okay. So, yes. I'm going to stop the recording. And I thank you all for attending.